Good evening. Welcome to week 4 problem solving sessions on regression analysis. I am Shreya, one of the TAs for this course, and today I will be discussing a few problems related to week 4 lectures. So before I start, please let me know if you can see my screen and if you can hear my voice. Okay, thank you. So I'll just get started. Fine. So just a brief recap on what we have learned so far. So far we have learned how to fit a simple linear regression. Okay, what is the aim? The aim is to minimize the residual sum of squares. So if we have a model like this, y equal to x beta plus epsilon, we would have predictions from here which would be denoted as y hat. So these would be your predicted values, and residual sum of squares would be alright. So this would be the residual sum of squares. What is the technique? Do you remember what was the technique? So what did we do? We used minimization, plain and simple minimization technique. So if we had, let's say, p unknown parameters, we differentiated this residual sum of squares with respect to each of the p parameters. So I would write here p naught del p1 to del pp, let's say, RSS, and we would equate it to 0 and solve these simultaneous equations to obtain the predicted values of the coefficients. Okay, so this is how we did. Then we also learned the properties of the regression coefficient, that they are unbiased, and the other properties, what is the distribution they follow, what is the expected value, what is the variance, those things we learned. Then we learned to test the significance of regression model. So what was that test? Can you tell me the hypothesis? Okay, so let's say we had a model like this. Okay, we had something y equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus epsilon. Okay, so this one, testing the significance of regression model. So testing significance of regression model, for this thing the H naught was that neither of this are predictive. So essentially none of the predictors are of use, or together they are not explaining the regression, the response at all. So the H naught in that case was beta 1 equal to beta 2 equal to beta 3 equal to 0, versus H1 was not H naught. Okay, this was the null hypothesis for testing significance of the entire regression model. Then we learned the the testing of hypothesis of individual regression models. Okay, so then individually this was actually an F test, which we can also obtain from the ANOVA table. Okay, then we learned how to test for the testing of hypothesis of a subset of regression coefficients. So let's say if we wanted to test whether beta 1 equal to 0, or if we wanted to test whether beta 2 equal to 0, or if we wanted to test, let's say, beta 1 and beta 2 equal to 0. Okay, so these individual tests were t-tests. Okay, and this one was also an f-test, which we learned how to do it based on the restricted and unrestricted residual sum of squares versus unrestricted sum of squares, or rather we would write it like this test we learned by the extra sum of squares techniques. Okay, so all of these have been discussed in previous classes or previous weeks. So if you have any question, please let me know now, then I am going to proceed. So far, do you have any problems or questions on these methods which were already discussed in previous lectures? No questions. All right. So then we also learned about confidence intervals. We learned how to test for hypothesis. We also learned about 95% or 90%, how to construct confidence intervals for unknown either predictions or parameters, and then using those confidence intervals we also learned how to test for the null hypothesis. For example, if I say if my h naught is such that beta 1 equal to 0, and I construct a 95% say confidence interval for beta 1, like that beta 1 is contained in, let's say, minus 0.02 to 0.03. So what would be the decision? Would it be to reject h naught, or or I would rather say do not reject h naught? So what should be the decision if such a scenario is given? No, it wouldn't be reject. It would be to accept. If the confidence interval contains your null value, then it means what? It means that, so in this particular problem, beta 1, we are 95% confident that actual beta 1 lies between these two bounds. Okay, so if we are very sure that it lies between this and this, then we do not have sufficient evidence to reject this possibility. So then the decision would be do not reject h naught. Am I clear? Yes. Okay. So that's the thing. If we, whatever null value we have, if that is contained within, so here I'll write it down, if value of unknown or rather estimated parameter is contained in 1 minus alpha percent confidence interval, then we do not reject, or in other words, not entirely correct to say, but accept the null hypothesis at alpha percent level of significance. Okay, so this is what we have learned so far. Now the next question is, how do I decide on the number of variables? Which ones to choose as predictors? So we'll have one y, one response, and we'll have a pool where multiple factors are there which could be predictive of y, which some could not even make justice in predicting y. But then because of certain matrices, we might say, okay, maybe this is useful. But the objective here is very, very simple. Our objective in fitting a linear regression those are very, very basic and very, very simple. We want, the first thing is, we want a model which predicts well. Okay. The second thing is, this model should approximate the true relationship between the variables. Okay, and we want to, this is the concept of parsimony, we want lesser variables. Okay, we want less variables to explain variation in y. Okay, and we want to use that variable which would be, so in essence we want to use a reduced model with 1 and 2 properties. Okay, so this is the entire motto behind variable selection. All right, so keeping these in mind, what can we do to select which variables to use and which not to use? Okay, so there are two broad techniques. First is, we specify all possible regressions, calculate matrices, and then we decide. And the second one is sequential selection, that we follow a certain chronology and then land at our model. Okay, so sequential selection will be described and questions related to this would be addressed in the next class. Today I'm going to focus on variable selection techniques when we have a wide array of regressions and we are going to use matrix like this: R square, adjusted R square, MS residuals and Mallow's CP criterion. Okay, so using these four, we'll ultimately decide which one is giving us a better prediction. Okay, so as illustrated in the class, so the first one is, let's say, R square. So now if we have, let's say, k minus 1 regressors, so then the model would look like this: y equal to beta naught plus beta 1 x1 plus beta k minus 1 xk minus 1 plus epsilon. Okay, and we would have fit how many models in total? Can you please unmute and say? K. Can you give an example? Which example do you want? Please feel free to unmute yourself and speak, since there's nobody. Yeah. Which example do you want? Can you please specify? This whole process. A little more specific. Choosing the best pair among a set. Yes, that is what I'm telling you. How to choose the best set of predictors from a set of variables. So let's say, okay, I'll give you an example. Yeah, actually all the problem I am Simon, so if I unmute you won't be heard or anything due to the background noise. Okay, but okay, for multiple courses, are you taking multiple courses which have all meetings at 4 to 6? All right, okay, fine. All right. So then, as an example, let's say I would use this thing. Okay, price of a house. Let that be your y. And there could be so many criterias which could influence the price of a house. X1 could be your floor area. Okay, X2 could be let's say how old the building or apartment is. Okay, X3 could be number of grocery stores within 1 kilometer. Okay, X4 could be number of banks Okay, nearby. X5 could be number of any other thing, let's say. Mm, something which is relevant but not so much. So let's say number of what do I say? Let's say motor training schools. Okay, X6 could be, let's say, whether if there is any metro station nearby or not. Okay, so this could be a dummy variable. So all of these are important criterias in determining price of a house. Now if we yes, exactly, there could be intuitively correlated, and the best practice would be to take everything, but then that would harm the concept of parsimony. We want a simple model which would predict well. We don't want something which would over predict. The main idea of fitting a regression is that it should be generalizable uh, to a fairly large extent. Now, here, what the main goal is to find a subset of these which would most uh, appropriately explain the variation in y, but we want lesser number of variables than these 6. Okay, so there could be so many other factors also. One idea is take everything together and make a very heavy model, but that would usually lead to overfitting. We don't want that. So we want to select a subset, okay, and then use that to predict y, so that if we are given the same variables in a different context, we are able to predict the value of a price, the value of a house more accurately. Yeah, of course. Yeah, go ahead. I was thinking about the age old issue of hiring new employee, which these days are still about doing some test and finding out who is the best at something. So in this scenario, which one is your response? What do you want to predict? Whether that person will be selected or not. Correct? Alright. So please let me know if there's something else you're thinking also. I was thinking of bettering this process, that is to not only find the best skilled employees, to find the effect of his or her joining in company's journey. Oh, all right. So as far as I understand, these two processes are a little different. So the first thing that you were talking about, I'll just copy your query and then see if I can answer it. So this is your question. All right. So here, this problem, I can think of it as a regression problem. How? Just give me a minute. So this problem, I can say that you have some tests, alright. So let's say you have x1 to x10 tests. Okay, so this one is assessing your punctuality. This is assessing, let's say, something efficiency. Okay, this is suppose assessing number of productive hours. Okay, or something. You also have some other, let's say, tests which assess your personality, x4, x5. Okay, so some personality related things. Okay, let's say one is assessing your memory span, one is assessing your attention span. All right, now this problem can be fit into a regression model such that, so the goal can be to find out a subset y equal to some fxi plus epsilon, okay, such that given a set of scores x1 to x10, based on a subset, you would be able to take a decision of whether to hire or not to hire. Okay, so this problem I can understand as a regression model. So here the model would essentially be it would not be a linear regression model, but it would be something like log p by 1 minus p equal to beta naught plus beta 1 x1 plus beta 10 x10 or x beta 100 x100, where p is the probability of hiring individual I, let's say. So this is your model, pi by pi xi x1i to x100i. Okay, so this is your probability of hiring someone. Now this entire thing would be your full model, that is, you use the entire battery of tests. Okay, but then this has some problems in the sense that if the number of individuals you have the data on, that is less than your number of parameters, then there would be problems in estimation. So then what do you want to do? You want to select, or rather prioritize, some features from the test. So let's say out of all these features that you have, you want a man to be punctual, you want to be efficient, you don't want memory that much, you want attention. Okay, and also another thing is productive hours. Okay, so then after using the selection methods, or rather applying those variable selection criteria that was discussed in the class, you should be able to land at 4-5 features, selected features, and then implement this to hire your personnel. So once here the variable selection techniques that we are discussing would come into picture, that from a full model, so from here from 100 we are finally coming to, let's say, x1, x2, x3, x4, x5. So from a 100 predictor model, we are reducing that space to a 4 predictor model such that this accurately predicts whether an individual will be hired or not. So then when you move on to implement this technique, so implementation will have this model, that y equal to beta naught plus beta 1 some punctuality plus beta 2, let's say what was the efficiency, plus beta 3 productivity, plus beta 4, what was the other one, let's say attention span, plus epsilon. Okay, again this would be log p by 1 minus p. And then you estimate everything, and then you find out whether you classify an individual, whether that person will be hired or not. Okay, so this is the first model that you were trying to say, and from whatever I got from your words, this is that problem. Now coming to the second one, thinking of bettering the process so it will not only find the skilled employee here, but also find the effect of his or her joining in company's journey. So this one is not that straightforward. I don't think it can be that straightforward in addressing, because if you want to track whether a person is skilled or not, and whether that person is affecting company's growth or not, main thing is you want to assess if they are contributing to growth or not. Okay, then that's a different scenario. So for that, what you can do is that, so if let's say delta y is your change in revenue, okay, and I'm talking about a very simplistic case. Let's say delta y is change in revenue, and in a year, let's say, so you're assessing performance, let's say. So then you can fit this as, suppose you have 100 individuals, okay, all independent, beta 1 x1 plus beta 100 x 100. So then from here also you can, because variable selection would essentially capture the variance in your revenue, all right. So in that case, variable selection I don't think is the best process to go about it. What you can find out very simplistically is you can test for significance of a subset of individuals or some individuals individually, so as to understand whether they are contributing to positive growth, or they are contributing to or they are not contributing at all. Okay, so you can test for a hypothesis that beta equal to 0 versus beta, let's say negative. Okay, you wouldn't want you would expect a positive outcome, positive impact or positive contribution, but you wouldn't be very harsh towards an employee if the contribution is not significantly positive. But if it is detrimental, then that is a cause of worry. So maybe you can go ahead with testing this sort of a hypothesis, and then find out who is making good contributions to your company. Okay. Yes, this is too qualitative, so we need to make a choice of quantitative matrix. Yes. And here whatever you are saying, so here the variables could be performances of existing employee in a similar role, competitor, future journey of the company, quantify this, no sales of a product. Yes, that is what I'm saying. So if you, this thing, yes, so you could, if someone comes with an experience, yes, so in this case you can take this experience as some metric and then find out whether they can be hired or not. But in order to track the future journey, you that I think is will not be this straightforward, that you have to give the I mean, of course you can take a call from here, like based on the, if there is some metric which assesses how much a person has contributed to, you know, to the growth of the previous company, then maybe we can fit this model. So if y, let's say, is the, or rather contribution to a revenue can be a proxy for that can be your increment. Okay, if a person has contributed positively, they would get an increment, a certain percentage of increment. Okay, so if I have, if each individual I, okay, they would have a y x1 to xp. So here they could have the performances, all right, here they could have their personality and work ethics, okay, some score addressing these things, and this y could be their last increment in the previous company. Okay, so then, sorry, this last increment can also be taken as another predictor. So using these predictors, we can assess whether we should hire somebody or we shouldn't hire somebody. But then this, out of all the pool of variables, we have to use some statistical techniques to assess which of these predictors would actually give me a better screening method. Okay, please let me know if you agree with me. If you don't, all right, fine. So this is the entire context in which we should perform variable selection. Now coming back to the lecture sessions, so today I'll be discussing these things, what, how to, I mean, pinpoint number and which predictors to use based on these four criteria or characteristics. So the first one is R square. So here, as I said, you have k minus 1. I will just try to write it like this. Let's say I have this y variable, which is, let's say, price of a house. Okay, and we have x1 to x6 variables. So I can do one thing. First is, it doesn't depend on anything. This is the null model. Second thing is, it depends on one each. Okay, only 1 parameters. Then we take 2 at a time. Y equal to beta naught plus x1 plus, beta 1 x1 plus beta 2 x2 plus epsilon. Then we take 3 at a time, and so on. So all, if we have k minus 1 predictors, then we will have in total 2 to the power k minus 1 regression models. Alright. Okay, this could be a $1 million digital project if someone comes up with such rigorous models. Yeah, of course. Okay, so now that we have 2 to the power k minus 1 regression models, we are going to see how to reduce that 2 to the power k minus 1 space to actually find out what could be the optimum number of predictors and which ones could be those predictors. Alright, so I think it's better if we do it with an example. So let's just get on to it. Okay, so here we have 1 gram of cement, heat evolved in calories. This is my y, and it's a function of 3 ingredients. These are the names x1, x2 and x3. Okay, I think something else was also there, I missed it. Okay, so in total we have 3, x1, x2 and x3. So based on the value of r square, which of the following models would you prefer most? Okay, so now here in case of r square, so one thing is r square p increases with p. Okay, so if we have a model like this where x1, x2, x3 none, and pairwise x1, x3, x2, x3 and x1, x2, x3, we can most surely say that this one would give me the maximum r square value because it involves 3 predictors, okay, or rather 4 unknown parameters. So if nothing is mentioned, then the full model best r square would be given by the full model. But again, we want to keep it as simple as possible. So the next best option is this thing, okay, r equal to 2. Now we have to find out which among these 3 would give us the maximum r square. Okay, right, now r square is how much? R square will be calculated as 1 minus SS residual by SS total. Alright, so in this case, which is the SS total? SS total is this one, total variation. Alright, because so when we have predictors, we partition it into SS due to regression plus SS due to residuals. Here for this none model, this SS regression part is actually 0. Nothing is explained by any regression model. So entire SS residuals would be my SST. Is it okay? Right, they gave best 3 candidates out of 8 technically possible models, apart from having all of them. What was the context for this one? Yes, Yes. So out of all the 8, uh, yes, that's true. Out of all the 8 possible models, we are going to find out the best ones, apart from having all of them, of course. Yeah. So now we'll have to calculate. So this would be, so for this model r square x1 x2, it would be 1 minus x1 x2 is how much? 57.90 by 2715.76. Okay. For this one it would be 1 minus, same thing, SS residual x1 x3 would be 1227 by this one 2715.76, and here for x2 x3 also it would be 1 minus 415 by 44. So the best model would be given by x1 and x2. Okay, because see, this thing is remaining fixed, SS total, right? So whichever is having lowest this thing, 1 minus this quantity would be highest. So then the answer is model containing x1 and x2. Is it clear? P proportional to SS residual. Yes, yes, P is proportional to SS residual. Inversely proportional, yes. So R square P increases with P and SS residual P would decrease with P. Right. So then moving on to the next one. So now the thing is, we have this model, y equal to beta naught plus beta 1 x1 plus beta 3 x3 plus epsilon. Then what is the value of Mallows CP? Okay, so the CP value would be SS residual when we have x1 x3 by MS residual when we have the full model minus n plus 2p. Okay, so SS residual for x1 x3 would be 1227.05 0.07, sorry, divided by MS residual full model. So full model is this thing, x1 x2 x3. MS residual is SS residual by degrees of freedom. Okay, so this one would be SS residual full by DF, and N would be 13 and 2P would be 2 into, how much would be P? Would it be 2 or would it be 3? So P is actually 3, because this corresponds to the number of parameters that we are estimating. Okay, so here we would have 3. SS residual, we know it would be this one, 48.11. And degrees of freedom, how do we calculate that? So full model would be beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus epsilon. So how many parameters unknown do we have? 1, 2, 3, 4. So df would be n minus number of unknown parameters, that would be 4. So this would be 13 minus 4, that is 9. All right. Fine. Then this would be 1227.07 by SS residual full model containing 3 parameters and another excess. So n minus 4, 13 minus 4 would be 9 minus 13 plus 6. How much does it come to? Sorry, did you ask anything? No. So this is what I would like to state. So this would be 1227.07 divided by 9 minus 13 plus 6. It is 129.34. Don't know why this option is not given here. Alright, so whatever this comes, that is your mallow CP. Got it? Okay. We'll move on to the next one. This thing. A hospital surgical unit was interested in predicting survival times in patients undergoing a particular type of liver operation. Random selection of 54 patients, so n equal to 54, was available from each patient record. Following information was extracted from pre-operation evaluation x1, x2, x3, x4 are the predictors, and different 2 to the power 4 16 different possible subset models that can be formed with these 4 predictors, right? Then there are the regression models with one regressor, two regressors, and so on. Value of coefficient of multiple determination is this. What is the R square value for this model? Beta naught, beta 2, beta 3. Again, this is very straightforward. R square, finding R square. You just have to take beta x2 and x3. Alright. And then for this one, you would have R square as 1 minus SS residual by SST. Okay. So this would be 1 minus 4.312 by 12.808. So that would be so it would be 0.6633. So that is 66.3%. Alright. So I'll just move on to the next one. This one. So consider data in problem 3 based on the value of coefficient of multiple determinant. Which of the following do you prefer the most? Same thing, we'll just calculate for A, x1, x3. So SS residuals would be x1, s3 is for x1, x3 it is 5. For B it is x2, x4. So for B it is 6.6622. I'll just copy this. So for B, this is x2, x4. So that means B is this thing. Okay. C is x2, x3. This is your C. And D is x3, x4. So this is your D. Alright. Now, coefficient, we want R square. Okay, R square increases with P and SS residual decreases with P. Here P is the same. So we want that model with the lowest SS residual. So the comparison is between this one, this one, this one, and this one. So x2, x3 we can see is having the lowest SSR square. So x2, x3 is the best model. Okay, that is option C. Or I should write it in different. So here, yes, x2, x3 lowest SS residual. So then answer is option C. Alright. Okay, moving on. Here, the value of the Mallow statistic CP for beta 2, x2, x3. So here also CP would be, here P would be how much? P would be P would be 3. Okay, so this would be SS residual x2 x3 by MS residual full minus n plus 2p. So again x2 x3 residual is how much? That is 4.312. So here we would have 4.312 divided by MS residual full. MS residual full would be 3.084 by how many number of predictors? 1, 2, 3, 4. So then if we have 4 predictors, then DF would be how many? DF would be 54 minus 5. Okay, and this minus n should be 54 plus p, number of unknown predictors 3, so it should be 6. Alright, so then if we calculate this, how much do we get it as? 4.312 into 49 divided by 3.084, this thing, minus 54 plus 6. So this is close to 20.511. So this would be this thing, 20.52. Yes, P is 3 because we have 3 unknown parameters. Alright, fine. Then we'll move on to the next one. Again, it's the same thing. Based on the mallostatistic CP, which of the following models would you prefer the most? Now, I want to tell you one thing. In case of CP, we always we make a plot like this. Okay. So, then we'll have one CP equal to P line. We want to take models which would have values lying very, very close to this line and with a smaller p. So we would want smaller p such that CP is approximately equal to p. Okay, so if we plot the CP versus p for all our models, we should be in a position to select only those variables which are towards this end of the graph. All right, so now if I come to calculations, x1 x2 x3 x1 x2 x3 x4 x1 x3 x4 x2 x3 x4. So yeah, I'll just bring it over here. So in this case, we are going to calculate for each of the cases the CP values separately. First thing I'm going to calculate is the MS residual. Okay, so that is how much? That is 3.084 divided by 49. Okay, and then CP is SS residual. So CP for A would be, SS residual is how much? 1, 2, 3. This is 3.109 by MS residual 3.084 by 49 minus 54 plus 6. For B it would be 1 to 4. So this thing 6.570 by 3.084 into 49 minus 54 plus 6. Oh, 1 second, this won't be plus 6, this would be plus 8, because 2p, here p is 4, 3 predictors and the intercept. Okay, so in this case this would be 8. Okay, for C it would be Cp equal to 134, 4.968 by 3.084 into 49 minus 54 plus 8. And this one for D it would be 234, so it would be 3.614 by 3.084 into 49 minus 54 plus 8. So I'll just calculate these quickly and then we have to take a decision. So this one, the first one is 3.39. Okay. Second one is 58 point something 38. Third one is how much? This is 4.968 into 49. This is 49 divided by 3.084 minus 54 plus 8. So this is something 32.93, and this ultimately is 3.614 into 49 divided by 3.084 minus 54 plus 8. So this is something 11.42. Now we'll only take values such that Cp is close, Cp that such that Cp is closer to P. So in this case P is 4, so this one is the closest to 4, and that is why we are going to consider model A. Is it clear? Alright, so then what else do we have? So consider the problem in this data in problem 3. The value of adjusted coefficient of multiple determination, so adjusted R square we want of this thing. So adjusted R square is actually 1 minus ms residual by ms total. Okay, so that is 1 minus ss residual by n minus p, where p is number of unknown parameters. Okay, divided by sst by n minus 1. So this would be 1 minus n minus 1 by n minus p, 1 minus r square. Okay, or I can write it as 1 minus n minus 1 by n minus p ss residual by ss total. So here would be 1 minus n is how much? N was 54, so this is 53. P is how much? P is here 2. So n minus 2, 54 minus 2 would be 52. SS residual for one single variable x4 is 7.409, and SST is this thing, 12.808. All right. So then what is the thing? 53 divided by 52 into 7.409 divided by 12.808, 1 minus of this. This is approximately 0.4104. So this is 0.41. Okay. Fine. Again, they are saying based on the value of adjusted r square, which of the followings would you prefer the most? The same thing. So we have to just find out 1 minus n minus 1 minus n minus p ss residual by ss total. So for A it would be 1 minus 53 by, so here P would be 4. 53 by 50 SS residual. Let's find out. So here this is x1, x2, x3. Alright, so here x1, x2, x3 is 3.109 by 12.808. For B it is 1 minus 53 by 50. One two four is 6.570. For C it is 134, 4.968 by 12.808, and for D it is 234. 234, that is 3.614 by 12.808. So let me just calculate. So this is 1 minus 53 into 3.109 divided by 50 into 12.808. First one is 0.74. Okay. Second one is 53 into 6.570. So this is 0.45. Third one is 4.968. So this is actually 0.588, and D is 3.614. So this is 0.70. Alright. So here, based on all of these, we see that model A is better. Now, the thing is, given your P is fixed, it's not changing, then everything apart from this number is going to be constant. Only for this case, since P is not changing, SS residual is the only variable factor over here. So in case you see that P's are all equal, then you can directly make a call saying that this adjusted R square value would be inversely proportional to the sum of squares due to residuals. Okay, but you absolutely cannot say this if P is also changing within your options, because then there would be a trade-off between this reduction in SS residual and reduction in the degrees of freedom. Okay, so be very careful, don't take such decisions when P is changing. The safest way is to calculate and get the results, but during exams, if you see that P remains same across all options, then you can directly take a call based on sum of squares due to residuals. But very, very importantly, if P changes, do not take that risk. Calculate every adjusted R square possible, and then finally base your answer on that. Okay. So are we clear on how to find out adjusted R square, MS residuals, R square, and those things? Yes. So now that we are clear on that, I would like to show an example in R, okay, so that you can understand how to get these plots easily. And this is not exactly part of your exams, but you can just give it a try to explore. All right, so first I'll stop the screen and share my R console. Please let me know if you when you see it. Okay, can you see my screen? Yes. Okay, so here first consider this data. Okay, okay, so here we have this data on different states in the US. Okay, our response is life expectancy. And we want to find out how life expectancy is related based on these other predictors. All right, or in other words, which of these predictors actually affect your life expectancy. All right, please let me know if the data set is clear to you. Okay, so now what we can do is we want to fit a linear regression on all possible um, regressors. Okay, so what we are doing, we are fitting this, we are using this lm command. All right, so lm, the syntax is we use lm y on given by this curl. We can specify the number of variables x1 plus x2. By default the intercept term will also be there. Okay, and we can mention the data equal to name of the data frame. Okay, all right, so this is the usual syntax. Now if we have something like this, dot, it means that regress y on every other variable in the data frame. Okay, that is what we are doing over here. Now if we do that, we'll get this full model. Okay, so this one actually is your full model, where so these are your beta estimates. Okay, beta naught, intercept, beta 1, beta 2, beta 3, beta 4, beta 5, beta 6, beta 7. All right, so just a minute, I'll just copy this here so that you know it. One second. All right, can you see the PowerPoint now? I hope you can see it. Okay, so this is your full model that we have. So if I have to say which is if I have to formally write down the model, then this y equal to beta naught plus beta 1 x1 plus dot 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 plus beta 7 x7 beta 7x7 plus epsilon. So then this one is actually beta naught, this is beta 1, this is beta 2, beta 3, this is beta 4, this is beta 5, and this is beta 6. Okay, sorry, so 7 parameters you have over here, so we'll have 6 betas. All right, now full model, your R square value is here. Okay, full model, this is the R square 0.7362. The adjusted R square is 0.6922. Okay, this F statistic is your test for significance that of the entire model, that is beta 1 equal to beta 2 equal to beta 6 equal to 0. This is that test statistic. This is the F critical value that you need to find out. Okay, this is observed F, this is F, the degrees of freedom of the F statistic that would be used to find out the F critical value, and we'll see that F observed exceeds F742 alpha, that is the upper alpha point, and the associated p-value for this entire regression is this thing, which is less than 0.05. So we can say that this regression is valid. All right, now we can see from here that population is somewhat significant. We have to look at this column. Okay, p value. So this is your estimate beta value, this is your standard error. Okay, standard error of beta, and this is your observed t value for each of individual tests. So h naught beta I equal to 0, those test statistic values are here. Okay, and this should be compared against a t distribution with degrees of freedom n minus p. So in this case it would be t n minus 7. All right, and this is a two-sided test. We'll just figure out from this column whichever is less than 0.05, they have been marked with a star. This is the significance codes that you receive. 1 star corresponds to less than 0.05, 3 star corresponds to less than this thing. All right, 0.001, and so on and so forth. Dot signifies that it is below 0.1. All right, now so here we have fit the entire model. Now here what model dot matrix is going to give me is the X matrix. Okay, so if you remember, when we were fitting multiple linear regression, we had y equal to x beta plus epsilon. Okay, so x was that column 1 1 1 1 1. Then for x1 we would have values over here, for x2 we would have values over here, x3 we would have values over here, and so on and so forth. Okay, so this matrix we can obtain by giving model dot matrix and the fitted linear regression. That is what we have done over here. Okay, So model dot matrix G comma minus 1, what this is doing is it is removing the x intercept term, and we only have from x1 to x6. Okay, so that is stored over here. All right, so if you see x, everything apart from the intercept is stored over here. All right, now, and the y value is this life expectancy thing. Okay, 69, 68.3. Now if we use this leaps command and we load this library far away and we plot cp plot equal to g, then can you see this diagram? So if I copy and paste over here, so this is your cp versus p graph. All right, and here I want to keep this thing. Now from this graph, if you can see carefully, this is your cp versus p line, this line. All right, and we see we should check for points where p is low. So our criteria initially was that to look for points where p is low and cp is close to p. So from here we see this point 4, 5, 6, this one 2, 3, 5, 6, 2, 4, 5, 6, here they are closer. So here we have p equal to 3 or rather 4. Yes, here we have p equal to 4. Here p is close to 5 and here p is close to 1, 2, 3, 4, 5, 6 something. So it is close to 8. All right. So from this thing we can see that 4, 5, 6 is the best predictor. So which are the 4, 5, 6 models? Then the x's are beta 4 was this hs.grad, 5 was frost, and 6 was area. So then out of this pool of 8 predictors, or rather I would say 7 predictors, we see that if we take these 3, 4, 5 and 6, HS grad, frost and area, then we are good enough, because the mean error of prediction which CP predicts is actually, it is as good as fitting the entire model. All right, so then we can go ahead and just fit those modified model and see how the adjusted R square is changing. Okay, so if I do life expectancy on hs.grad for frost and area, so this would be hs.grad plus frost plus area. Okay, and I name it as G1. And if I give summary G1, let me see if the metrics are good or not. So here if we go see, then R square value is decreasing, adjusted R square is also sort of decreasing, but the overall model remains significant. Okay, so maybe some of the it's not that if one metric is giving you some result, all other matrices will also converge to the same result. What you have to do in such cases is that look for multiple evidences and then go with the one which suits your purpose. Okay, so if the criteria is that so if the concern is that you want to estimate, you want to have something, so what I want to say is that if your concern is to have a model with what do I say, with least mean prediction error, then we would go for the CP equal to P criteria. Okay, if you want to do variable selection and see whether, and if you have decided on P, let's say, or something like that, so if you want to select, if you want to see, so let's say this is one such example. Let's say you select one base model like this using CP, and then you want to keep on adding a few more relevant variables. Now R square is going to change as you increase the number of variants, but R square bar might or might not change. Okay, so here like we used x1, x4, x5, x6. Now in the revised model we want to use x4, x5, x6 and let's say x3. Then we can compare with adjusted R square for this model and the adjusted R square for this model. If this is giving me substantial results, maybe I could go forward if I do believe that inclusion of this variable is very, very important. Otherwise, I could also skip it as well. Okay. So, just to show you how this CP versus P plot looks like. Okay. So, maybe from this plot, if we have to conclude, then probably this is the best model. Okay. All right. So I hope this was clear. If there's anything else that you would want to discuss, please let me know. So instead of this CP equal to P graph, you could also have, like sir mentioned in class, you could also plot, for each P, one second. So here, instead of the CP equal to P, you could also plot P 0, 1, 2, 3, and your max r bar square. Okay, or 0, 1, 2, 3 p maximum of r square for each of the models. So for here x1, let's say if I have the entire model as x1, x2, x3, x4, then p would go up to 5. Alright, so then p1 would be only 1 predictors. If you use, calculate the adjusted r square, plot it. Okay, the maximum of those. And now if you see, yes, and now if you see that for 0 it's nothing, for 1 it's increasing, let's say here, for 2 it's here, for 3 it's here, for 4 it's here, for 5 again it is decreasing. This can also happen. So in such cases we have to, if I am given a choice, I would select p equal to 2. And then among all variables or all models where p equal to 2, which means so among those I am going to check this SS residual. Whichever has lower SS residual, that would be my model for selection. Okay. But for r square, you would notice this pattern would increase but will never decrease. Okay, maybe the increase will not be very prominent after a certain point, but it'll either plateau, but it'll never decrease. So take that plateau, that point where increase is not that substantial, and then take all the models in that space with that p and see whichever has the maximum r square value. Or similarly, instead of r square, you can take minimum ms residual. Okay, for p equal to 0, 1, 2, and so on, and whichever. So here you can find it will decrease, and from some point it is going to increase as well. It might increase. Okay, so you have to take then that position where this frequent change is happening. So which is giving the minimum ms residual, and then among all the variables or all the models which fit that p, you will have to take this one. All right. Yes. Okay. Yeah, it is approaching 6, and I also have to end this session. So thank you so much for joining. I hope I have answered some of your questions. If you have further questions, please get in touch and post it in the discussion forum, and we'll take it from there. Thank you so much once again for joining, and I'll see you in the next class.